we? CCLA difference what? Difference makers, greatness clap. Hey, greatness clap. You're the difference makers and it don't stop.
But let's get started. And I'm going to use the mic the whole time for the folks who are online to make sure they take the audio too. So I remember the mic in one hand and the clicker in the other. But I am Allison Gosno. I work at the Contra Costa County Office of Ed. I'm the math coordinator there. And I've had experience. I've been an administrator for a while now. I was a high school assistant principal. I was an administrator over instructional technology. And then I've both been an elementary school teacher and a middle school teacher. And also I was a math intervention teacher in a middle school, primarily for 8th graders. So this topic's really near and dear to my heart for folks who work in the setting of middle and high school in particular. So often we have students who are really struggling with not internally really understanding some of that fundamental, especially 4th and 5th grade kind of number sense. But then what do we do when we're in secondary where it's not built into our curriculum? It's easy to say, right, I don't have time to do that. So this topic's really near and dear to me. And the presentation is uploaded on Sketch. It's also, there's a link there and a QR code, so you can get it. You don't particularly need it for right now, so you can get it however you need it. As I'm talking, right this minute, we're not going to go over that problem on the right with the blue arrow. However, we're going to refer to it later. So if you want to fiddle with it, think about it, sketch it. There's a favorite person. You want to use the little notebooks. But we will refer back to it, and you can solve that without any calculator. So with that in mind, we will get started. Just a really quick, I'm just curious in terms of who's in the room. How many people in the room are in the classroom? Directly work with kids. Okay. And how many people are outside the classroom, whether you're TOSA administrator, district level? Okay. So we're half and half. And for folks in the chat, feel free to put your job role in the chat just to kind of see. So we're kind of half and half here. So today we're going to cover 3 main objectives. First, really briefly, what the research says about making connections, the importance of making connections to knowledge. We're going to look a little bit at how developing number sense is in the California Math Framework, K-12. So especially those of you outside of the classroom, if you're supporting districts or sites that are thinking about adoption, where is this in the framework? Because it's very clear that it's in the framework. And so looking for that in new curriculum, if that is something that your districts are doing. And then we'll spend most of our time on tasks and routines that you can use to leverage prior knowledge, to help students develop their number sense and then also accelerate their learning. So the ultimate goal is to give them, secondary students, more access to the grade level content, more success in grade level content. So really quickly, just in terms of what's the research say about making connections to prior knowledge. For those of you familiar with John Hattie's studies, he studied, many of you probably are, but all sorts of things we do in education and how do they impact student learning, student growth. And so the farther to the right, the farther in the red on this scale is the bigger the impact that it has on student learning. So integrating prior knowledge was found to have a huge impact on students doing well in grade level material. His studies, you can sort of get there from his visible learning studies below, but just so knowing the importance of integrating prior knowledge, using it in the classroom has a huge impact on student learning. And so it's a really big part of the California Math Framework. And I like this imagery just because it's outlined in chapter 3 of the framework that developing number sense is a piece of all of what we do, K-12. It's not just an elementary school idea. So this just gives you an idea of kind of what are the big ideas of each grade band, and then just kind of think about where I might develop students' number sense in relation to each of these things. And we'll do some things today, sort of thinking about how to make connections to some of these big ideas that are outlined in the framework. Chapter 3 of the framework is all about developing number sense. And one of the things that it says is it's imperative that students implement a standard method only after they have fully developed an understanding of the operation, can connect previous strategies and representations to the steps of the algorithm, and make sense of this abstract process. This goes on to talk a little bit about elementary example of this, but I think it's really important that we remember and that we share with teachers, for those of you who are working with teachers and outside of the classroom, that this is just as important in middle and high school as it is in elementary. So it's not simply about like what the second part talks about, like base 10 concepts, though that's also very important, but that we're doing this in middle and high school. The framework kind of has a lot of information in chapter 3 of why that's so important. That we're not just teaching kids how to multiply binomials by a rule, but that they really have some conceptual awareness of what this is doing and how multiplying binomials or factoring, like how does that work in the same way that multiplying two digit by two digit multiplication height worked in 4th and 5th grade. And so the more that we can kind of connect back these concepts we teach in middle and high school, the more kids have this hook in their head to where they put the information. So the chapter 3 of the framework has a lot more about that, if you're curious. And if you are interested in kind of like having more of a research background on fluency and developing number sense, I love this book. Is anyone familiar with this book? Well, a couple people. Okay. So this book, it's listed in the bottom of the slide, but the authors here, Jennifer Bay Williams and John San Giovanni, they talk about procedural fluency, which to me has a lot to do with like developing number sense. It's not just your times tables, right? It's like these 3 big buckets. So efficiency, how efficient are you in choosing a strategy and implementing that strategy? Flexibility, so I know various strategies and I know when to use them. And then accuracy, the importance of getting it right. This book has been really instrumental for me, especially in working with site leaders, working with teachers, so that I kind of understand a little more of like the foundations and the research behind why this is important. So I really love this book for that reason. So what we're going to do now, we're going to do a bunch of math together. And as we're doing it, kind of put yourself in the head of whatever context that you're in, but like, if I'm that 8th grade teacher, or I'm that 10th grade teacher, or I'm supporting that 10th grade teacher, or I'm supporting that site admin, or I am the site admin, right, of that middle or high school, kind of how would this help with the kind of things that we teach every day in those classes with that upper grade secondary content? So we're going to do a bunch of math. We're going to kind of debrief it as we go. So we'll start with number talks, which I imagine many people know about. Can you just like show of hands, who's done number talks, knows the number talks? Like almost everybody. Okay, not everybody, but many people. So I purposely chose some different approaches to number talks. Those of you who know about them, you may know this book. This is like my favorite book. I have a slide with it as well. There's sort of some more, what do you want to say, like standardized way to do them. We're going to do some different kinds of ways that are in this book to sort of think about how it might complement, again, the secondary math content. So number talks, sometimes called math talks, they're designed to highlight a particular type of problem or useful strategy to advance the development of efficient, generalizable strategies for class. And then many math talks are still very applicable, not just in elementary school, as sometimes they're more commonly thought, but in middle and high school to lay that groundwork for algebra understanding. So that's in the framework. That's in chapter 3 of the framework. So it refers back to these number talks. So there's the book if you're interested in learning more from it. Here's what we're going to do so here's an example of a number talk. We'll kind of run this a little more like in the traditional number talk way, and then we're going to do some that are a little different than what you might have experienced for those of you that know about them. So, and if you're online, you can put your thoughts in the chat too. So here's what I want you to do is I want you to think about 3/8, okay? And is it more than a half or less than a half? And how do you know? And what I'm going to ask for this first one, we'll kind of do it in the more, like I said, traditional number talk way. So once you know if it's more than a half or less than a half and can explain why you know, if you can just put one finger on your chest, okay? And then once you've done that, if you can think of another way to explain it, put a second finger on your chest. If you can think of a third way to explain it, put your third finger on your chest, etc. I'm just going to like stop talking for a minute and let you think about what are ways you might explain how you know if 3/8 is more or less than. So go for it. So it looks like everybody in the room has a way. Again, if you're online, feel free to put how you're thinking about it in the chat. So I'll write a few of these down. All right, who would like to explain one of their ways? How you know more than half, less than half? Yeah, can you tell me your name? Stephanie. Stephanie. Okay. I'm just gonna put S just to save time for Stephanie. If I was with real students, I'd write the whole name, but I'm just gonna do that with you guys. Yeah.
I kind of thought that usually is for half of eight.
So you asked yourself, is 4 half of 8? Okay, and what made you know that 4 was important? Because it's half of 8. Yeah. It seems kind of obvious, right? But like, okay, so that 4 is half of 8. So you're really looking, this is like, this would be the halfway point, right?
Yeah.
This would be the halfway point to 8. Okay? So you asked yourself, is 4 half of 8? And then what did you decide? With this.
3 is less than 4.
So 3 is less than 8. So 3 is less than 8. So you concluded that it's more or less than a half.
No, less than 4.
I mean, thank you. 3 is less than 4. Thank you. 3 is less than 4. And you concluded then that 3/8 is.
So it has to be less than.
Okay. So 3/8 is less than a half. Okay. Great. Please. Just by show of hands, who did it more or less like exactly the same way? Great. Sort of. Okay. Tell me your sort of.
I actually thought it that way first, obviously, and then I also thought of like taking it on a physical object, pizza, for example, cutting it in half or cutting it into eight pieces and only pulling out 3 pieces that actually is not meeting half.
Great. So tell me your name.
Daniel?
Daniel. All right. Good. So Daniel thought of it like a pizza. In general, pizza come round. I love working with fractions with rectangles and find them a little easier to manipulate. So are you okay if I make a rectangular pizza?
I was really, no, I'm joking.
You live with it for today? Okay, I appreciate that.
No, totally.
Okay, so tell me one more time. So we got our 8-slice pizza. Yeah.
And a rectangular pizza. And
Appreciate that.
yeah, and so cutting it in congruent part, equal parts, and 4 out of the 8 would be the top half. Or the left 4 pieces, and then really taking away 3, you still have a little bit greater than a half.
Okay, so this right here,
Yeah, we'll do the vertical, yeah.
this right here is
Yeah.
half the pizza, and you're saying so, but we only have 3 pieces,
Yeah,
and so 3/8 is less than, than 1 half. You're gonna use the less than symbol then. And I love, Daniel, how you wrote or said that we needed, if we were to draw a visual, we needed equal size pieces. Okay, who did it like Daniel did? Kind of thought of it visually. Yeah, sort of, yeah. Is your way some of what Stephanie and Daniel said or something different? So I thought you were kind of a sort of.
Instead of just visualizing what I had it compared, like I had 2 bars and I split 1 bar in half and the second bar into 8s, like, and lined up that half mark so that you could physically compare what half a bar would look like and then what your 3/8 bar would look like.
Okay, when you say bars, like just like.
Like rectangle, sorry.
Rectangle, okay. So something kind of like this. I added a 0 and 1 just to make it for everyone else to kind of see. So like this, and then this one you divided into 8 pieces.
Yes.
Okay, so like that.
Yes.
Okay. And then you said you took 3 pieces.
Yeah. And I just colored in 3 and then half.
All right, so 3 pieces is less than half. These should be lined up, sorry. And tell me your name.
Shanae.
Shanae with a C or a S?
S.
Okay. All right. So anyone else think of it like Shanae?
good.
Did you think of it? Did you think of it like this at all?
I did also.
Kind of, yeah. Okay, great. Any other ways that either you did or you can think of how you might solve it, or anyone in the chat? Does anyone have anything different?
Not fully different, but I think they're all resonate with the fact with the equivalent fractions that 4/8 is equal to a half, therefore 3/8.
Great. Okay, thanks. Yeah. And I was thinking like maybe 5 people, but making a call denominator. Okay, so tell me more about that. to triangulate the two of the 1/2. Yeah. Okay. So you're saying that I have 1/2. But what I really want is eighths. So I can compare it to eighths. Okay, so how would I get there? I would figure out like what do I have to multiply the 2 by to get to 8? I know it's 4. But what I do to the bottom. Okay. That. So I did 2 times 4 makes 8. And how come I can do to the bottom what I did to the top? What number is like this altogether? Because 4 and 4 is 1. Because 4/4 is 1. Okay, so if I multiply anything by 1, I'm gonna get the same thing. And so then I have 1 times 4. Okay, so I know that 1/2 is the same as 4/8. And so how did that help you? Or how could that help you? And then I can look at 3's. I have the same denominator. Yeah, so now that I have the same denominator, it's a lot easier to compare. Okay, 3 of them is definitely less than 4 of them. Okay. Do any of these pictures, Shanae, right?
Mhm.
Daniel or Shanae's pictures remind you, do you see any of what Stephanie did down there in either of these pictures? Like, do you see the changing like a 1/2 to 4/8 or a representation of it as 4/8? Yeah, right. So like here's my 4/8, right? So I can say this is 1/2, but it's also 4/8. Same thing here, right? Like here's my 4/8. Okay. Great. So let me keep that there for a second. We're gonna do a few more. I'm not gonna talk it through like I would if I were teaching students with all of them, just for sake of time. But I want to look at some other examples, and then we're gonna talk about like how does this help when you're that 8th grade teacher, or you're that 9th grade teacher, or you're that 11th grade teacher. So let's just leave that there for a minute, and we're gonna move more quickly through these other examples. But I think they're good to kind of like at least get in your head. So other ways you could do this. There we go. Okay, more or less than a half. 8/5. So I'll give you a minute. You don't need to do the thumbs. We'll just kind of like talk these out for a second. Any thoughts of just looking at even these 4 models, right? Let's say we did this problem another day, like tomorrow. But like, do any of these models help you explain how you might justify if 8/5 is more or less than a half? Or tell me what I'm going to do.
I'm thinking about Shanae's bar, the 2 of them for me, the parts. And I'm thinking about how you can see the number of pieces, especially in the bottom one, the number of pieces is the same as the denominator for the whole thing.
Mm-hmm.
And like if this was a whole, and it's filled all the way out into 8/8 pieces. And so having 8/5, the pieces are there's more pieces than there is space.
Yeah. So I could, again, if I were in the classroom, I'd have this on the wall, I'd keep it so you could see it somewhere. But like, I could use that same idea that now I have something, I'm going to divide it into 5 pieces.
Mhm.
But actually, I think we keep going, right? If here's 5 out of 5,
Mhm.
right? There's 5 out of 5. And so I need another 5. I didn't draw that very well because I'm going to fall off the page here. But 6, 7, 8. So here's 8/5. But I could use a similar model, right? Like here's 0 and here's 1. But now I'm dividing it into 5 pieces. 8/5 is somewhere way over here. And I could think about that in terms of my half, right? But this is like one of those that for often students look at that and they're like, no idea what it's talking about. But we can refer it back to one of these other models. And we could refer it back how it does. We could think about the pizza model, right? And we could sort of think the same thing, like instead of this 4/2 was 8, like how would we use Stephanie's way of thinking about this to reason through this? I don't want to try that out loud. Like Stephanie first went and thought about like what is half of, right? This one was 3/8, right? So she thought about what is half of 8. So what would I ask myself with that model? What's half of 5? Right? So half of 5, oh, that's 2.5. So definitely 8 is like way more than 2.5. So you could take any of these models and apply it to something that's like still not, this isn't secondary math per se, but it's definitely math that secondary students struggle with, many of them. Right? Okay, so let's look at any comments so far.
No comments, but a
Yeah.
question. So when you said number talks, I initially raised my hand, but I was thinking, choral was, math. When you, when the students, teacher facilitates, what the students are saying a sequence of numbers.
So like world count.
Total counting. that's what I
Yeah,
was thinking.
like count by 1/2, like
Right,
start
right.
at 3/4 and count by
Yeah, and
1/2,
then,
there's
yeah.
halves, there's-
So
Yeah,
I did not know this, but now I get it.
great.
So it's good that you went to the original and now we're gonna do the variation, right?
Yeah. So one, a way that like, for those that are familiar, like you kind of traditionally see it is like students giving different methods, writing different methods. I think the nice part about this is that using this for harder content, right? Like these models, all these ideas that came up, like has to be equal pieces. Finding half of something is like finding half of the denominator, having some visual models, finding common denominators, right? Like you can't solve those two-step equations with fraction and coefficients and all that stuff, right? You need to find common denominators. You need to know how to like get rid of the fractional coefficient, all these things. So it's like these different ways of looking at it, I can refer back to for something that's now relevant to like what we need to do to solve our two-step equations today. Okay, here's another way of thinking about it. 2/5. Closer to 0, closer to 1/2, or closer to 1. It'll get harder. So I'll give you a second. Same thing. You don't have to do the thumbs. Like we'll just kind of talk about it. Feel free to write. And there's some for anyone who doesn't have scratch paper and the little notebooks. There's some note cards on the table, or just think about it, whatever you want.
Able to sound to be right on the mic.
Oh yeah. Thanks for the reminder.
Should we do everything all over again?
There's not a restart.
Sorry to everyone online. We're gonna restart with the microphone. Right. So let's just hear like one or two again. We're not gonna do it in like a formal sort of number sense way, but of like, how did you think about it? Anyone willing to share how they thought about it? And I'm coming to you with a mic, so you should still share. Okay, thanks, Steve.
My brain got to decimals, right? Because it's 2.5. So I was like, okay, it's closer to 1/2. But I can see some of the students wanting to lean to 0 because they would say like 1, 2, 3, 4, 5. Oh, so it's 0. So it's just 2 ways of thinking.
Yeah, okay, so let's talk about that for a second. So changing it to a decimal. Okay, that's a huge secondary concept, right? And also, as secondary teachers, often we don't want them to, like, when you're solving equations, I was always like, no, leave it as a fraction, just trust me, like, leave it as a fraction. But when you're uncomfortable with fractions, students often want to change it to decimals. But then there's other times where you really want it as a decimal. So wait, let's talk this through for a minute. So 2/5, if I were to change it to a decimal, how would I do that? What's like a happy decimal denominator? Yeah, go Lord here.
It would be really great if it was tenths. So you can turn it in 4 out of 10 and 4 tenths.
Yeah, like it would be really friendly if it was over 10, right? So 4 tenths would be, and now I'm coming back to what Shanae said in the beginning here, right? Like this skill right here, right? But if we, so 2/5, if I get back to my other paper, here it goes. Okay, so 2/5. If I multiply by 2/2, I'm gonna get 4 tenths. So this is the same as 4 tenths, right? And that then, and this is what you were saying, right? And like, so now I can also think about like, okay, half, I can be stuck in this idea here, right? Half would be 5 tenths, like what's half of 10? And so what would 0 be? How many tenths is 0? Zero, right? So if I sort of make a number line and make this 1/2 and this is 0, where's 4/10 gonna be? Closer to the 0 or closer to the 5/10? Closer to the 5/10, right? So yeah, so it is closer to that. But you can think about like all those different models that we had, right? And where you might go with that and how often that comes up. Like, I want to change it to a decimal. Great strategy, right? Like, really great strategy. And then I can sort of bring it back to like this fractional stuff and say, yes, change it to a decimal. And I didn't even change it to a decimal here, right? But we can then go with that, right? And then we can say like, oh yeah, okay, that's what the decimal is going to be. Go.
I could also see students switching to money because it's.
Thanks, Beth.
I can also see students switching to money because it's like they probably have greater experience using money. I have $5, $2, which one are those into? Is it half? If it's half, I have $2.50. So I gotta go do the half.
Yeah, and that's like teaching that flexibility with number signs is so important. Like, who cares? Don't leave it as a fraction. Change it to a decimal. Change it to money. Like, do something that have the flexibility to know, like, oh, this is the same as a decimal, or this is the same as a money example. I'm gonna do that, and then I'm gonna like come back to this to give my answer, which is like close to 0, close to 1, right? Yeah. Okay. Any other thoughts on that one? All right, let's look at a couple more. Make it a little harder. Closer to 0, closer to a half, closer to 1. When I come back, all these original strategies actually are useful.
So you're saying we did a good job, right?
It's a great job. Yeah. Gold stars. I will be sending postcards home to all of your parents. So let's just hear like there's maybe one person on it, but do any of those 4 original models help as a way to think about this, or did you think about it totally differently? This one's harder. Which one is are you sure that it's not? 0. Okay. Like, I'm sure it's not 0 because it's more than a half, right? 31 is more than 20 and a half. That makes 41. Okay, so it's more than a half. I'm sure of that. And so the question is, so it's not 0. But is it closer to a half or closer to 1? Anybody want to take a chance? Yeah. Okay, 70.
I think it's closer to 1 because I found that half of 41 is 20.5 or 25 cents. And then I just subtracted, so 31 minus 25 cents is 10 and a half. But from 31 to 41 is only 10, so it's closer.
Okay, well now you have my microphone too. Hold on a second. So I'll grab the microphone back. Cool, like, here we go. Okay, all right. So say it one more time. I heard you, but now I want to break what you said.
So I figured out what half 41 was, so it was 20.5.
20.5 out of 41. Okay, or 21 and a half. Yeah. Okay.
And then I just found the distance from 1.5 to 31.
Okay, so 31, hold on one second. Yeah, so 31, 40, I have no idea where it really goes, but it's in here somewhere, right? Okay, so you found the distance from 21 and a half to 31 was how much? 10.5, okay? Wait. I think it's 21, sorry? 20 and a half. Oh, there we go, thank you. Good thing I have you guys to correct me. Okay, now it is 10.5. Okay, great. Okay, and then this one whole would be how much? How many 41sts? 41, right? So there's my one whole. Okay, and so how far is it from here to here? 10, right? From 31 to 41 is 10. So which one is it closer to? Only 10 spaces from here, but it's 10 and a half spaces from here. So this is the closer one. So it's closer to the one.
Hmm.
Interesting way to think about
Yeah.
fractions, right?
Yeah.
You could do this with a lot of what is, I mean, you could do 1 minus this and this minus 1/2. You do a lot of long calculations, but this, we don't have to do a lot of long calculations. We use what Dell said, which was change it to a decimal, that was sort of a quicker way we could do that math, right? I, as the teacher up here, was let me put it back as a fraction, but still say, yeah, the decimals was actually a really easy way. Maybe that's what my head did faster, but I'm gonna leave it here because I need to keep it in fraction world. But again, taking a fraction, these fractions don't look that hard, but if you change the prompt that you ask, they all of a sudden become hard for us as adults who live in a mathematical space with kids and educators. Right? And so you don't have to always be doing the high school math that looks like the high school math to be really pushing kids' understanding that they can apply to that high school math that really looks like high school math. Yeah.
Are you talking to Mike?
I probably.
Yeah.
I'm sure we'll appreciate it. So yes.
Should I whisper? So what I thought of was obviously, not even obviously, no, 3/4 is 75%, and 30 out of 40 is also 75%. And since 31 is just greater than 30 and 41 is just greater than 40, then it's got to be closer to 1 than the half. And I did it by, I guess, rounding using the tools of rounding.
Yeah.
And see.
Yeah, and these problems that are right on the cusp of 75, 5%, you'd have to really think for a minute, is 31, 40 first just more or just less than 75%? I'm sure that students would get it wrong. And so it's taking problems, just choosing numbers that are right on the cusp of something really pushes students thinking. And I guarantee you, if you were to sit down with a group of adults, that they would really struggle with it, right? Even adults who were oh, I did just fine in algebra 2 or something. And so I think taking the time to really wisely choose the numbers you want to use can really push older students thinking. Yeah.
I was just gonna say also, at first, I actually didn't want to do the 31 to 40 over 40 places, right? But when you said thinking of the strategies that other people were using, that was super helpful because then I got back to what came over there was the west half of something.
Yeah.
And I did it that way. But so I had a strategy because you talked about stuff.
Yeah, that's a great point. And often, so it's that's saying prior knowledge. I might start with that 3/8 example. Not because I'm gonna spend hours and hours with my 8th graders on is 3/2 more or less than a half, but because I know it's gonna lead me to these more complicated conversations. And I know that a lot of my students, without starting with something to hook it on, can't get there. And so I think there is a space for going back and using examples from upper elementary or lower middle school. And I think the fear is always no, you should never use those problems because the fear is I'm going to spend the whole class period now just on this. And I agree with that. You want to be making sure you are always leading to the grade level material, even with students who struggle, even if you're in an intervention setting. But having these simpler models that then you as the teacher can sort of make sure we've got some things. I'm actually really glad at the end, Stephanie, you threw in this other one, because sometimes the denominators are just too complicated. We just need to find a common denominator. And so having these as this hook to then build on for these harder examples. Yeah, thanks.
These seem to be
No.
these seem to be very low floor, high ceiling kind of problems. You could bring this to the high school level kids, even calculus kids, and talking about approximations and getting closer and closer and closer to a specific number.
Yeah.
So I could not.
But I could use this absolutely in higher level numbers.
Yeah. Yeah, for sure, right? There are those like calculus examples and how you're gonna like find this area under a curve and you're gonna slice it smaller and smaller and smaller. And that's what this formula is gonna do for you, is gonna add up all those little slices, right? Like here we are slicing it smaller and smaller. And like, at what point would I be exactly at 3/4, right? You could do the same logic of, is how far, you know, how many steps was it from 20 and a half, 41st, right? From half to one. You could do the same thing of like, what if I ask this question, is it closer, is it less than 3/4 or more than 3/4, right? That's like really tricky and leads to these like, I have to slice it thinner and thinner and thinner to actually know. Yeah. So I'm just gonna show you a few more. I'm not gonna give you like the time to calculate them all. They're in the slides, obviously, so you could use them or go calculate them for fun tonight if you wish. But so some more, just similar ideas, changing your language, right? Which is greater. Take two fractions, which is greater. You could easily find common denominators and do that. But you could also justify it in some similar ways of like the size of the pieces, right? Is a 7, well, how are those slices bigger or larger than fifths? And if you have one of each of them, well, is it the bigger slice or the smaller slice? But then you're going to have someone who's going to say, well, I just found, 30 fifths, like it's common denominator, and that's how I did it. But other ways to think about it. So those two numbers, is there some less than 4, equal to 4, or greater than 4? Yeah. Again, right on the cusp. It's really close to 4, I'll tell you that. I'm going to keep moving here, but like, so taking things that are really close to something, and then like, how are you going to slice them, brings out all these different strategies that, again, like can naturally lead to some of the work you're doing in higher level math and in high school math, and kind of referring back to that. Okay, before I start with a new structure, any other thoughts, comments, just of those kinds of examples? Yeah.
I think in math especially that we emphasize having one way of answering or coming up to an answer, and that the few examples we just had just showed, how valuable it is to be able to come up with multiple strategies in solving it or coming up with an answer.
Yeah.
There's no one right way. There's multiple ways of getting to that answer.
Yeah, and and the thing I would add to that too is I've been in a lot of settings recently. I was with a parent group. I've been in districts recently where some teachers and parents say like, just teach the algorithm, like just teach one way, you're confusing everybody. And like, I understand where that's coming from. I'm sure if you were working in math settings as a leader, you've heard this before too. Like, I completely understand where that's coming from. And I would argue that like some of those problems, like what's the algorithm to decide like this one, let's see if I go back. Like, I guess you could find common denominators to do that. Like that would be the algorithm, right? Is find a common denominator and add them. I am quite sure that would take far longer and way more like potential for making little calculation errors than if you had the reasoning to think through it. And you can absolutely like reason and think through this to figure this out. And that doesn't mean that everyone should always do it that way, but the more we're helping our older students in secondary, like not just like rely on like all these different calculations, but be like, pause, like let's think about this for a minute. Instead of just always going straight to that algorithm. I think we're really pushing and broadening those problem solving skills. Also in just giving them the agency to be like, okay, yeah, let me think about this for a minute. So yeah, I appreciate that. Okay, so this particular structure, I learned from a webinar from a friend of mine, Howie Hua, who some of you might know. He posts number science problems daily and does little TikTok videos on them. A link to this webinar is in the resource guide, the Launchpad. So I highly recommend it. It was co-sponsored with Innovamat, which is one of the curriculum companies. But Howie just taught me a lot in that webinar of some of the ways he thinks about things. So this structure is HUA, Hua. And there's a link in that the Launchpad to that webinar. But he does like a daily, like 90-second little number talk. Yeah, they're so good. I see them on Facebook, but I think they're all over, like on TikTok. Yeah, and he's local. He lives in Fresno. So how does knowing blank help us with blank? Okay, so How does knowing, if I tell you 5 times 8 equals 40, how does that help us know what 6 times 8 is? I'll give you a second just to think how you would approach that. As a side note, I could do this like a number talk, right? I could like hear your strategies. I could write them down. I could put your names. I could map them out. I'm not going to do that again just for time. Like any of these can be done in this sort of traditional number talk sort of way. We're going to just more have it just. But, so who has an idea? Like how does knowing 5 times 8 equals 40? How could that help you figure out 6 times 8?
If you told me that there's 5 groups of 8 is 40, and I'm trying to figure out how much 6 groups of 8 is, I would know I just need to add 1 more 8 to get 48.
So yeah, 1 more 8 would give me 48. Anyone think about it differently?
Same thing. Okay. It's kind of the same as you're saying, if I was just like thinking of these groups, I would just add another 8 to them.
So just adding another 8. Again, like if you, this clearly is like an elementary school problem. You could do this with elementary schoolers, like it'd be wonderful. But I want you to kind of think about, I'm going to have you answer that in a minute or two, but like how this might connect to things you teach in middle and high school. Okay, but starting here, the same way we started with that 3 8s, but took it in some complicated ways. Starting with a just like thinking about multiplication in a different way. Okay, so here's another example. How does knowing, if I tell you that 400 divided by 8 is 50, how could that help us do 392 divided by 8?
And same thing for folks online. If you are not already, but you want to throw those in the chat just so you can see each other's thinking. Anyone here want to share how they would do that? Right here. First, I was like, 392, what? And then I realized that 392 was 8 less than 400. So I thought, that's when you divide it by 8, you're going to get 1 less 8 out of there. So it must be 49. Yeah. Yeah. Right, but a different way to think about division, right? Not just like, oh my god, let me grab my calculator, or oh, let me like do the long division, and da da da. And like how it wasn't obvious, right? You were like, wait, so it's 8 less, so I guess that means I'm gonna get 1 less 8 out of the 50. It makes me think about remainders, right? Like when we're dividing or getting something out, like we divide things and have remainders in all sorts of ways. Not just in elementary and middle school, but then in
High school, math, right? And so like, and we have to think about and interpret what the remainder means. And this really helps you, like how many, oh, okay, I'm getting 1 less 8 out of this other thing. So it can kind of lead you to those different concepts in middle and high school where like that all comes up. Any, like thinking about middle and high school concepts, do you feel like where you could go if you started with the multiplication or the division, but can anyone think of an example where you're like, oh, I could use this in this way? Yeah.
I mean, when you introduce like variables, if you're like, okay, knowing 400 divided by 8 is equal to 50, well, what about 392 plus x divided by 8 is like equal to 50? And just see like, oh, well, x is, oh, it's 8. Like just having them break down that numbers can be broken down, because in elementary, they do number bonds. They do that. They just don't do it with gigantic numbers that we can now use in high school.
Yeah. Nice. Thanks. Any other connections come to mind?
Maybe in trigonometry, like the coterminal angles, figuring out like the full rotation of a circle is 2 pi in radians, and comparing different like radian numbers and actually saying, well, if this is the amount of radians, you know, let's go 75 pi over 7. And what is that? What is its coterminal angle? And you keep subtracting 2 pi. And so instead of that, having 2 comparisons and saying, well, if you know this is 50, what would this be? And you can see, well, the very next difference of numbers is, rotated by pi or 2 pi, then you can maybe put it on.
Yeah, nice. And so this idea, I think it's like trying to get students away from like, I always have to just do the rote calculation, but I'm like, here, let me give you something. And then the student has to figure out how is that useful for this other thing that I'm trying to solve, which is, Lori, when you explained it, you were like, first I had to figure out why that was useful. And once I did, oh, that was really useful. And so I think like being able to use our math knowledge or support math teachers to use their math knowledge to think about like, how do you take something that's like a little bit simpler than what I need to do, but create a structure that I can then apply to this more complicated thing. Is that whole like kind of teasing with the, like, that's where I can infuse the earlier content. Okay, one more structure. And all of these are either from Howie's webinar, which is linked, or they're from this book. So both of these can really like open your mind to other ways of thinking about it. So we're gonna do one more thing on this kind of trend. And this one's called share, share, compare. And it comes out of this number talk book. So for this one, I'm gonna have you solve on this paper just a few problems. So if you have paper, if you don't, grab one of those index cards. Hopefully folks who are on Zoom, you have some scratch paper you can use. I'm gonna give you a moment, and can you solve each of those problems on your own? And then just be ready to share your strategy with somebody else. And this one, I'm gonna have you actually like get up and share with somebody. So I'll give you a couple minutes. I don't want you to feel rushed. So take like 4 or 5 minutes, we'll check in. But solve each of those. And just think about how you're doing, and then we'll share. That's weird. You could do like 30 more seconds, and if you don't finish before, you know. So the strategy is called share, compare, and it's just about having students use with any problems you want, but having students just have the opportunity to explain their thinking and hear different ways of thinking. So what I'm gonna do is I'm just gonna pair you guys up. So if there are already two at a table, you can stay where you are, and maybe the three of you guys, if you don't mind being just a group of three. And if you can just take, I think for time's sake, we won't do all of them, but why don't you as a group decide on two problems, just the same two, I don't care which group. And just take a turn where each person explains how you did it, okay? So just do two of them, whoever two you want. And for folks in the chat, if you just want to share how you did any of them and just see each other's strategies, that would be great.
It's still salty, but
Yeah, not just like.
what I did was some similarities here. Forex. The 8 is double the 4. The 4 is a 4 to 16. So what I did was I said between half the 4 plus 2. And then I know, like I was like, oh, I did notice something and I thought maybe we could keep going down, so. Yeah, reduce that, so I guess would be double that, and then this number here, that's your cheap. That by 4. Like, no. And then I can go down and be like, this will be 80 more manageable. And it's not flexible, so I think it's making sure they know that. That's, you know. I'm gonna quadruple. So I took out the 410. Yeah. That's where he is. Breaking them times and what you. Is there a complicated? At first I was like, okay, they know what I mean, they're like, this place to get right there. So then I became dark, was even get go back, so there's not basically like more equal, which like you're not sure. And then I did the kids, I think it's going to be the next 20 months, and that was like this is we go to like 20 about and it's happening. And I was like, and then I like have to like this happened. So then I did like busy, You made a little box, like a little area box.
But then when you draw that picture, right?
Yes,
That's
and it's
why
really,
I where you'll find like 20 here and that's 2020.
Okay.
And yes. And that's what I had to figure out, right? It wasn't, I didn't know. But no, and how to change how I teach.
Almost like a.
Problem. But I have to. When you see the word.
You do it in the box away.
Yeah, I guess. Elementary math, maybe down there. It's educational way.
Yeah.
Yeah, we're actually gonna take a close up house, see what that very thing on the side. This side of the 21, I was sorry, I would call it. Like if you say, it's one. I have.
You're right.
Everyone on that side.
Okay.
You're on that side. Lightweight. It's on like. It's on
That's right.
Yeah, I can figure out.
They're just a dollar.
Then I realized show it out.
Jump in on.
What
This is like a. Well, I have.
1.20 and one more like. If I was to do different, it's actually like we're 21 by 20. Actually, but. We're right 21 out of 21. But then I ended up here, but we're always in 20 out of 25. This smaller, so it's inside. 400. So what is this chunk here? This. So I'm gonna have you guys just finish your last. So this is 20, and this chunk is 20. The left over right one, when they want to say 1 is 21. And then add all the chunks going. Probably a better word than chunk.
Yeah. Yeah.
This table over here is having the best conversation because it literally is what we're about to do next. So hold on to all of the thoughts.
Saying we're better than everyone.
2 gold stars. You really need those gold stars. Blue star coming all of you, and now I got 5 stars. I think I have some candy for you at the end too.
Nice.
Okay, so, just for the sake of time, we're not gonna like kind of talk about all the different strategies, but I'm just curious, like by a show of hands, and you can put it in the chat if you're online, like, did listening to someone else's strategies for any of these, like, make you think about the math in a different way? For whom did that happen? It happened for me just standing at this table. Yeah, so like, everybody here, lots of people online, it sounds like. And so I want to just sort of like again, you can choose whatever problems you want. Choosing problems that then are going to lead into something you're going to do, which in this case it does, in the way that I chose them, can be really useful. And it's just a reminder, Lori sort of brought it up earlier, but like hearing different strategies helps you be like, oh, actually that was really helpful. This table got in a whole conversation about multiplying binomials, which funny enough is the very next slide, which is where I was going to go with this. So good job like guessing where we were going. But again, like it can lead you into, okay, here's what we want to talk about today. And I started in a place where all my students had something to say, something to contribute, or got something out of this conversation. And now we're like, oh, what's going to come next? Like, I'm kind of ready to like take in whatever's going to come next. So here's what's coming next. So that's the share, compare from this book. So some of these, I realize the white font's a little hard to read in the back, but these are guiding principles for number talks. I'm not going to read or go over each one, but again, they're from this book. And I think that they also are echoed in a lot of what you read in the framework. So any of you that are supporting teachers, supporting districts, doing work around the framework, curriculum adoption, number talks, I think, really get to these guiding principles, get to a lot of the exact same things that the framework is leading to, and often are not as commonly found, especially in high school math teachers' classrooms. Like I think as the kids get older, teachers sometimes like hit on these various things, not whether or not they're doing number talks, less and less. And so just thinking about how do I create those spaces for discourse and flexibility with number, and that it's equally as important that my high school students are doing that than is my third graders in my district are doing that. So I'm going to move ahead. And this is also from chapter 3 of the framework, which is just saying a deep realization for students to explore in higher math courses is that objects of one type have relationships with each other that parallel the relationships that objects of a different type possess. And so it's really it says one of the earliest introductions to this concept of parallelism occurs for students as they compare the behavior of numbers to the behavior of polynomials. There's a little bit more in there that you can read on your own, but and that seeing polynomials is analogous to the way that the 4 basic operations work. We're going to talk about this for a minute here. It's exactly where this table sort of landed. They started looking at polynomials. And so this piece, like polynomials are such an integral part of so many parts of high school math. And how can we go back to what students more innately, hopefully understand about those elementary concepts, but connect it to like the depth of the high school concepts. So we're going to look at this for a little bit here. It'll be the last thing that we do. So this table over here was doing what I would call the area model or partial products. Excuse me. Often it's taught in elementary school, but not everyone in here. I'm just going to go really quick if you're not familiar with it. Some people call it the area model, some people call it partial products, some people call it the box method. Real quickly, can somebody talk me through that 18 times 22, like how I would solve that? If you know what partial products or the area model box method is. Yes, Cindy. Cindy, right? Yeah.
That the dimensions are 18 by 22.
Okay.
And then we just apply 22 and make a line to make 20 and 2, make it a little simpler.
Okay, so 20 and 2, yeah.
And then 18 is maybe like 10 and 8. And then, 10, now they're a lot further than right?
Okay.
Just getting all these like partial products or them together.
So 20 times 10 is 200.
And then
20 times 8 is 160. 2 times 10 is 20. 2 times 8 is 16.
add them all.
And then I'd add all those up. So it's going to be 200 plus 160 plus 20 plus 16. For all the people who are like, you just have to teach them the algorithm. Like, this is exactly what the algorithm's doing in a different way, written in a different way, right? This is just a different algorithm. Although like your purists would be like, just teach them the algorithm, for goodness sake. I wanna just, if this is new to you, I'm gonna move a little fast just because we just have 10 minutes, but I'm like assuming that many of you have seen this before. So a few thoughts on how this could lead to a lot of this work we do with polynomials and multiplication and all that stuff. So because I wasn't sure I was gonna have a whiteboard or anything to write on, I took pictures of this. Okay. So take a look up here. So this right here, this is exactly what Cindy said, right? This first one. And this is a way that's like commonly when it's taught in elementary is like break it up into tens and ones, right? Like 20 and 2 is 22, 10 and 8 is 18. Truthfully, you could do it with anything. You could make 22 out of like 17 and 5, and it would still work. Not as easy to do in your head, but it still works. So my two thoughts about this, in terms of this like parallelism of like how can I take elementary stuff and make it applicable to high school stuff, is this is absolutely would work. Like I said, so would 17 and 5, or 9 and 9 to make 18. That's just less friendly in your head. One thing I would say, no matter how you do it, and I would encourage your elementary school teachers, if you're working with them in any way, shape, or form, is actually encourage at a young age to put the plus on there, because the plus becomes important when you start doing it with variables. And in 5th grade, there's no reason why you couldn't do this instead, right? 18 is 20 minus 2, and 22 is 20 plus 2. A kid wouldn't necessarily think of that, but like teaching students that also is going to get you, that's also partial products. It's also going to get you there. But how does this, and this is why I would encourage even like if you're working with elementary to have them put like the 22 is 20 plus 2, 10 plus 8, because when you get to those variables, that becomes, like I said, important. Any high school folks, like what does this remind you of?
Difference of 2 squares.
The difference of 2 squares, right? Like all of a sudden we have x minus 2, x plus 2, right? And no, you're not going to teach the difference of 2 squares to your 5th graders. However, if you, as that high school teacher, start saying, oh, well, this is like the way you might have seen it in elementary, and they're like, oh, yeah. And you pose the question, could you do it this way? Do you get the same thing? Why not? Like impose that. All of a sudden, you're taking these elementary school examples, but you're putting the lens of high school math on it. And that these are going to both work, but not only are they going to both work, but like, oh, let's play around with using subtraction instead of addition, right? So that is one. And then the other is taking that second example that was up there, right? That leads really naturally into like, I might do this for multiplication. I might do this for factoring, right? Like I can undo if I had 2x squared plus x minus 15. But I've done enough of this that I know like, oh, the x squareds are always going here. The constant is always going here. This 1x is somehow getting taken care of in these, right? If you've done enough of them, you kind of internalize. CPM does that with their diamond problems. But taking, like kind of really thinking about, okay, how might I take this and go back to something you know from a long time ago, but link it to what we're doing now and thinking creatively about that. I think can be really powerful. I'm gonna just move along so that just we kind of close it up because time is about to run out. But there's a lot of fun you can have with those and just exploring and seeing what example might be useful. Like this one, right? Like, oops, sorry. I chose this one on purpose as a way to show like, yeah, this is probably what most 5th grade teachers would do. Like Cindy was perfect, right? What she said is like exactly the way that almost every teacher would probably model this and teach this. But as the teacher being like, oh, can we think about this a different way? And like, you secretly know this is super helpful for those Algebra 1 students and beyond. Okay, so in the slides, there's a lot of ideas for games and puzzles. I'm not gonna do any of them today, but I did put like a copy of different books that I really like. I think games and puzzles are the same idea. It's just letting you play with these things. It's like internally developing your gut feeling about them as students and just the ability to be like, let me kind of think about that. So some of my favorites that you can go explore. First, it is in the framework. They talk about the importance of using games and that like engaging students in math games. So it's also in the framework as something. I love area mazes. Has anyone heard of them? Okay, I love this book. If you are someone who likes on the side, like, you know, you do crossword puzzles or you do your Wordle and all the things, you do pips, some of your attempts, whatever. Check out Area Mazes. It's a very inexpensive book, even just for yourself. That problem that was in the very beginning came from this book. And it's all about finding these unknown sides and unknown areas, all of rectangles. It involves doing a lot of times tables, but the logic is really complex, even though you only need to know your times tables pretty much to do them. So that first slide, if you want to stay at the end and like, if you didn't solve it or you did solve it and you want me to tell you if you got it or give you a question that's pushed it, I will. But it came out of this book. Love this book. I also love these books. These are just books, you're just practicing your times tables, but in a sort of game, math gamey sort of way. So if you know, again, have students who need to practice their times tables, I love these. The junior edition is just simpler numbers. The regular one has a lot of decimal multiplication in it, so useful, just fun things to do, great numbers to solve as well. This is a new book that came out from Peter Liljedahl and Kyle Webb. It's building thinking classroom tasks, but a lot of them are just number sensitive. I really love this one. This book is specifically for 6th through 8th grade. So I really like it. Has great tasks to just work on number sense. And when you look at it, it kind of tells you grade levels. And this perseverance level is like kind of how challenging it is. So some are really hard. I find they're really complicated for me. Like they just push my thinking. I really like them. I love this one. And finally, Open Middle. Some of you probably know them, some of you don't. There's a book, there's a website, and it's all about you use the digits 0 through 9, and you can't repeat. So you have to use digits like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 to fill in this box to make something that works. There's a website that that has examples at every grade level, all free. So again, another thing that just like take the thing they're working on, but make it a little more complicated. And you can really like play with that developing number sense. So these are some of my favorites of other things to do. And finally, this quote also is from this book, The Figuring Out Fluency. And I really love it as a closure. So typically many educators have the unproductive belief that students with disabilities or students who struggle require being shown step-by-step processes with little or no attention to conceptual understanding or reasoning. What this talks about goes on to say is that students with mathematical agency see themselves as mathematical thinkers who understand what they're doing and feel they can solve a problem without you just showing them the steps, without you showing them how. That everyone deserves these opportunities to develop procedural fluency and develop a positive mathematical identity and agency. And I think for me, this quote really resonates of why it's important to build in these routines so that everyone in the room believes like, oh yeah, I'll figure this out. Like this is really hard. I have no idea what the teacher's talking about, but I can start. I feel like I believe I can figure this out. And I think the more of these kinds of activities you do with students, the more they just walk in the door of their class each day being like, okay, I'll figure this out. Like, oh, that was really hard, but I got this. And I think it's like the reason that we should say yes, like we shouldn't simply show an algorithm and step by step. Like, yes, there is a place for that. Yes, there is a place for having notes and step-by-step examples to refer back to. And that can't be the only thing we do. Like we have to develop students' agency so that they walk into the room every day believing they can do it. So with that, I think it's just about time to go. So I'm gonna not do this, but there is a feedback form up there if you're willing to do that QR code. We do have like a minute or two if people want to stick around, if anyone has questions to answer them. You need to do that first problem from the first slide if anyone wants. And other than that, thanks so much for having me. Yeah.